We ended class today on September 15th for our 12:30 class, a little bit behind the others, so here's a little bit of information that will help you finish your homework. So out of the Schrodinger's equation, we are able to now calculate what is the probability of finding an electron in a given volume. And what you'll notice, and we pointed out in class, is that the probability is shown as highly probable in areas with high color and very improbable in lower color areas, and there's actually these zero probability areas. So let's take a little bit closer look at these different categories of shapes. The first category is these ones that are spherical, and those are actually going to be referred to as s orbitals. Then there are these ones that are kind of dual lobed, those are p orbitals, and then these ones down here that have these crazy shapes are d orbitals. Let's dig into those a little bit more. For the s orbitals, they actually start appearing in the n equals 1, or the ground state shell. The probability distribution of finding them, or the area in which we're likely to find them, centers around the nucleus, and there's a higher probability closer to the nucleus. So instead of talking about, well, where's the probability highest, we can say, well, where is 90% of the probability? And we kind of draw a sphere around that. And then we kind of draw a cartoon version of that. And we say, well, 90% of the electrons are probable to be found within this distance from the nucleus. You'll notice that one of the things that Bohr had right was as we go between energy levels, energy n equals 1 to n equals 2 to n equals 3, one thing he did get right is that the distance in which we're probable to find the electron gets further and further away from the nucleus. However, it is a distribution within that that's different, and there's no literal orbit of the electron going around the nucleus. We can also look at plotting the probability electron distribution. This is a probability, part of the Schrodinger equation, how likely we are to find it. The more likely it is, the higher up it is. So this is the most likely that we find it, and that's at a distance of 53 picometers away from the nucleus. As we go further out, there's less and less. So that hard shell is going to say, well, within this distance, that's where 90% of that probability is. So in this case, that's about 100 picometers for n equals 1. And we can look at n equals 1, 2, and 3 for the 1s shells. And we pointed out earlier that there's a probability of finding it. Up here is the shell model. But down here, these graphs show the probability. And the really interesting thing is if we look here, there's actually places where the probability of finding an electron is 0. That by itself isn't too crazy. But then we look at the fact that on either side, we are likely to find the electron. That means that the electron can either be here or here when in the 3s orbital, but it can never be between. So this idea of how does the electron go from one side to the other is something that we can't answer anymore. If we did, we'd be able to say what the path is, and that the path crosses this no man's land in the middle here. With the p orbitals, they now have this dual lobe shape. There's a probability, 50% probability of finding an electron on this side of the nucleus, and 50% of finding it on the other side of the nucleus. However, there's an absolute 0 probability of finding an electron at the nucleus or in between the two lobes. Once again, using logic to work your way through this doesn't work, because there's no way in our head that we can logically say, well, the electron has a 50% probability of being here, 50% probability of being here, but it never is going to be between the two. The other interesting thing about the p orbitals, these dumbbell-shaped ones, is that there's actually 3. There's the one on the, we can arbitrarily assign a z-axis, an x-axis, and a y-axis. And if we look at this next image, this image here on the right, shows all 3 of these overlaps on top of each other. Now each one of these orbitals, the s orbitals and each of the individual p orbitals, of which there are 3, can hold 2 electrons each. And that's part of the Pauli exclusion principle. If we then look at the d orbitals, they have an even more interesting set of shapes, and each one of these 5 d orbitals can have a total of 2 electrons in them. So that, another interesting thing to note, is that the s orbitals start in n equals 1, p orbitals only start in n equals 2, and then the d orbitals start in n equals 3. So we can only have one s. We can't have we can't have one p or one d. Those do not exist. We also, so then we could have 2p, we have 2s, 2p, but not 2d. So d doesn't start until the third level. And remember that there's 5 orbitals within that, so that means it can fit 10 electrons. So the last part we talked about in class, in our first period today, was that Bohr's model of the atom did some really nice things for us. Bohr's model allowed us to say, well, electrons can either be at any of these different levels, these shells, but it can never be in between. So this idea of quantum is something that Niels Bohr really helped us figure out. But then the part that doesn't work so well is that these aren't spherical orbits around a nucleus where we can predict the path. And actually hidden within each one of these shells, n equals 1, n equals 2, n equals 3, is, so here's n equals 2 in Bohr's model, and here's what the actual more accurate version is that 2, the electron can either be in 2s or 2p, and any one of these 2p orbitals is acceptable. All of these are called degenerate, and degenerate just means they all have the same energy. This is completely true for Bohr's studies because he was studying hydrogen. And hydrogen, with no charge, only has 1 electron. And if we have 1 electron, then this model holds true. As soon as we look at any element, though, with more than 1 electron in it, we find that these 2 n equals 2 subshells are no longer degenerate. We can see over here that 2 electrons in 2s are more stable than 2p. And pause for a second and try to think about why that might be. And what we can rationalize is that if there's only 1 electron total, like in a hydrogen atom, it doesn't matter if the electron is excited from 1s up to 2s or 2p, that electron is going to be stable. However, when we have electrons both in 2s and in 2p, now we have these negatively charged electrons that are repelling each other, and that repulsion pushes those differently. So the 2p is actually less stable, having electrons in it, than the s. So now the next question is, what element is this on the right? Go ahead and pause and try to figure out what element is being represented by the description on the right. If you figure this out on your own now, the way that we would want to do this is that the number of protons defines the element, and this question says that we have to assume there's no net charge. So if we can find out how many electrons, we can say that those numbers are equal, and that we know from the number of electrons how many protons. And you'll notice each one of these electrons is denoted by a little arrow that has only half of a side to it. And so this atom here looks like it has 6 electrons. 1, 2, 3, 4, 5, 6. That means that it's neutral, it has 6 protons, and if we have 6 protons, that is also the same as carbon. So I want you to now pause, and I want you to think about what were the rules for filling these orbitals, the shells and the subshells. And then please watch the next video to get the last little bit you need out of this.